In this video, we will look at ways to use our relationships between pressure, temperature, volume, and number of particles to predict conditions of a gas after a change is made to that gas. So we're going to use what I call a PTVN table to organize ourselves as we go through and solve these problems. And P stands for pressure, T for temperature, V for volume, and N for number of particles. So as we read a problem, we're going to fill this table out identifying what we know. So first, a gas is allowed to expand from a 50 milliliter container to a volume of 200 milliliters. Those are my initial and final volumes. And it says the original pressure was 3,600 millimeters of mercury. Well, that is a pressure, so I'm going to put that in the initial pressure box. And it asks what the final pressure is, so that's what I'm trying to figure out. Our temperature and our number of particles are not mentioned, so that tells me that they are most likely held constant. And you can do as I did and put a line through those boxes if it makes you feel better, so that you know you did not forget about them or leave something blank. Now we're going to think about a relationship, and when most people see this problem, the first thing they think is, okay, volume got bigger. And I want to think about how volume affects pressure, the one that I don't know. Well, if the space gets bigger, there's a lot more room for particles to move around, and so they're going to hit the walls less frequently. So when volume gets bigger, the pressure should get smaller. And people tend to notice on this one that the volume just got 4 times bigger. So the volume got 4 times bigger, the pressure should get 4 times smaller, or it should be multiplied by a fourth. But I want to put this in a way that, use a problem-solving strategy that we can consistently use even when the numbers aren't as easy as they are here in this problem. So I'm going to take my quantity 1, and a quantity, remember, is a number with a unit, and we only have one number and one unit for pressure. So this is my quantity 1, and I'm going to multiply it by a relationship. Well, we're going to get our relationship from the variable that we know 2 pieces of. We know 2 different milliliters. And just like when we were doing unit conversions, we can write our relationship 2 different ways. We can write it as 50 milliliters over 200 milliliters, or we can write it as 200 milliliters over 50 milliliters. And we're going to pick the correct way based upon this relationship here. So the fact that if V goes up, we need pressure to go down. Of these 2, the one I'm highlighting here, 50 over 200, that is where the 1/4 comes from. And that fraction, because I have 50 on the top, that will cause my work to match my relationship. So if I do 50 milliliters over 200 milliliters, that causes me is basically taking 3,600 times 1/4, which is 900 millimeters of mercury. And if I kind of compare these numbers, this matches my prediction. Volume got 4 times bigger, pressure will get 4 times smaller. 900 is 1/4 of 3,600. The last thing to consider is sig figs. And if I look at my problem, this has 3 sig figs, 3 sig figs, 2 sig figs. So my answer should really have 2 significant figures. The only way to write 900 with 2 sig figs is 9.0 times 10 to the second millimeters of mercury. All right, we're going to attack our second problem now. In this problem, it says the tire's pressure is 24 psi, and then the driver adds air and returns the tire pressure to 32 psi, which is presumably what it should be. So our initial pressure is 24 psi. Our final pressure is 32 psi. It says there were originally 100 puffs of air. Puffs are the units of numbers of particles. So I'm going to put 100 puffs of air on the tire. It says how many puffs of air are present after the tire is filled. So no mention of temperature and volume. So I'm going to look at the relationship between pressure, which I know, and number of particles. And I don't need to worry about writing a relationship under the variable I'm trying to figure out. So pressure from beginning to end is getting higher, 24 to 32. And if pressure got higher, and I think about my relationship between pressure and number of particles, the number of particles must also have gotten higher. So these aren't it's not quite as easy to see the relationship between 24 and 32, but I can still use the same strategy. There's 100 puffs of air, and I'm going to take that quantity 1 and multiply it by my relationship. And my relationship can either be 24 over 32, or it can be 32 over 24. And based on what I know about gases, pressure getting bigger should cause number of particles to get bigger. And of these two fractions, 32 over 24 is going to get bigger. So 32 psi over 24 psi. So when I take 100 times 32 over 2/4, I get 133 puffs. So in other words, the pressure increased to 4/3 of its original value, and at the same time the number of particles increased to 4/3 of its original value. Last thing to check is sig figs. 24 has 2 sig figs, 32 has 2, and 100 with a point at the end has 3 sig figs. So of those, 2 sig figs is the smallest, so my answer with 2 sig figs and units will be 130 puffs. We are gradually increasing the complexity, so we're moving on to our next problem. In this one, we have a 600 milliliter sample of nitrogen. 600 milliliters milliliters are units of volume, and since it's heated from 30 degrees Celsius to 60 degrees Celsius, and the pressure is constant, so I'm going to cross that out. Number of particles was not mentioned, so I'm going to assume that's also the same. And it says, what is the final volume? So in our relationship, we're going to say temperature increased, because as we're going from 30 to 60, that's an increase. And if the particles go faster, but the number of collisions stays the same and the number of particles stay the same, then the volume has to get a little bit bigger. Otherwise, we'd get more frequent collisions. So when temperature increases, volume increases. And on this problem, again, you don't have to write anything in the relationship column for the one that you're trying to figure out. Our quantity 1 is 600 milliliters, and then we're going to multiply by a relationship to get our final volume. Now, the biggest mistake people are going to make is I watch students do it. They're going to say, 60 over 30. My temperature doubled. My volume also is going to double. My volume should be 1,200 milliliters. But that is not correct, because if you look back at what we learned about temperature, their temperature relationships are only direct relationships if we use temperature in Kelvin. So before you do anything else on a gas problem that involves temperature, you need to convert from degrees Celsius into Kelvin by adding 273. So 30 plus 273 is 303 Kelvin, and 60 plus 273 is 333 Kelvin. Now that we have temperature in the units of Kelvin, we can say, well, the temperature clearly didn't double. It went up by 10% or so. Volume is going to go up by about 10% as well. And we're going to make a fraction with 333 on the top and 303 on the bottom. And the reason for that is because we need a fraction that makes volume get bigger. So if we solve that problem, we get 659.4 milliliters. Now I've got to check sig figs. I notice that both 30 and 60 have 2 sig figs, and 600 with a point behind it has 3 sig figs. So of those, 2 is smaller, so I'm going to round my answer to 2 significant figures, so 660 milliliters. And again, checking, did my relationship work the way I think it should? Temperature got bigger by about 10%, and this looks like about a 10% increase in volume as well. Okay, we're going to start with our final example problem. This one we're going to up the difficulty again even just a little bit more. So in this problem, it says we have a gas at a temperature of 12 atmospheres. So our pressure is 12 atmospheres, and we've now seen example problems with pressure in PSI, pressure in millimeters of mercury, and now pressure in atmospheres. Remember, we have like 4 different units of pressure you should be able to recognize. Next, the volume is 20 liters. The temperature is 10 degrees Celsius, but I'm not going to make the same mistake as last time. I'm going to remember I need to put that into Kelvin and just put it straight into the table in units of Kelvin so I don't forget it later. And then it says I raise the pressure to 14 atmospheres and increase the temperature to 30 degrees Celsius, which would be 303 Kelvin. If I add 30 plus 273, that's where I'm getting the 303 Kelvin from. And it says, what is the new volume of the gas? So that's what I'm trying to figure out. No mention of number of particles, so I'm going to assume that's constant. I never want to put anything or never need to put anything for relationship for the one that I'm trying to figure out. This one looks like it's going to be different because this time we have 2 variables we don't know. And I always want to take the variables whose changes I do know and relate them to the one I don't know. So I'm going to look at what happened here. Pressure got bigger. It went from 12 up to 14. And I want to think about what effect that has or what relationship that has with volume. If pressure gets bigger, there's more collisions. That would happen if volume got smaller. So when I set up my relationship for pressure, I'm going to take 20 liters, that's my quantity 1, when I multiply it by the pressure fraction. Since pressure causes volume to get smaller, my fraction here should be smaller than 1 fraction. I'm going to put 12 atmospheres over 14 atmospheres because that would make pressure get smaller. Then I've got a second change. I can do this in 2 steps, so I could get an answer and then make another adjustment. I can do it all in 1 step. Now I'm going to think about the temperature relationship. Temperature got bigger, and if particles move faster, that makes volume get bigger as well. So because the effect of this relationship is volume getting bigger, I'm going to put my 303 Kelvin on the top and my 283 Kelvin on the bottom, because temperature and Kelvin and volume both need to get bigger by the same percentage. So I'm going to put all this together. I'm going to take 20 times 12 divided by 14 times 303 divided by 288. And when I do that, I get 18.35 liters. And I'm going to double check sig figs here. So looks like I've got 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs. So I'm going to report my answer with 2 significant figures. So it'll be 18 liters. Will be our final volume. But I want to point out to you something interesting on this one. Volume goes down, pressure says volume gets smaller. Temperature says volume get bigger. Well, volume can't get both or can't do both at one time. So the last question says which relationship dominates and why. Well, these are all really like percentage changes. So if I take 12 divided by 14, I get basically 86%. So that means like if 100% was no change at all, the pressure must have gone up by 14%, so the volume is going down by 14%. On the other hand, the temperature fraction, 303 divided by 283, I got, so 303 divided by 283, that's equal to 1.07 or 107%. So in that case, the temperature went up by 7%, so the volume also went up by 7%. And it says which relationship dominates? Well, the pressure relationship is going to dominate, and you can see it wins out. The volume did in fact get smaller. 18 is smaller than 20 because there was a bigger percentage change in the volume. So a bigger percent change, sorry, not in the volume, in the pressure than in the temperature. Temperature only had a 7% change, where pressure had a 14% change. And so the bigger percentage change is the one that's going to kind of win out. Now, volume didn't go down by 14%. The temperature kind of prevented it from going down quite as much as it would if just the pressure change happened without the temperature change. But overall, the volume goes down because the relationship between pressure and temperature, pressure and volume dominates because it's a bigger percentage change. Now it's your turn to practice.